Hello, and welcome to Ants Are Everywhere. We're taking a look at NFS, the network file system. Hello, Mustafa. And what is NFS? NFS is the network file system. It's a distributed file system that you can use to serve files from some server, such as a NAS, a network attached storage, and you can consume those files as if they were local files. They show up on your file system, you can mount them, and so on and so forth. I'm sure we can find a diagram. NFS is pretty old. I think 1980s. So here's a diagram. You have some storage here. I guess these are supposed to be like disk drives. And then you have some server. And then these are the clients. And so if you have a big company, like let's say Google, they might have started with having all of their code on an NFS server, and then no one workstation needs to have all of the code on their machine. They just have a virtual copy on their machine, and then as they like CD into different directories or build files that contain other files, the data for those files are pulled down from the storage device. Otherwise, they're just they basically just see the metadata. That's the basic gist. And we're going to take a look at how it's defined. So in the Linux kernel, first of all, let's do this. How would they resolve write conflicts? That's a good question. So let's have questions about NFS. So how to resolve write conflicts. An important one is going to be access. How is access determined? Where is it determined? I know that later versions use, I think Kerberos is really the only way to authenticate to an NFS share. And then once you're in that share, I don't know how, if you have access to everything or if it just uses the standard Unix permissions, etc., to handle things. Who knows? I certainly don't know. Maybe we can find some of that out. Can I take this file? Whoa. I've added tabs to Emacs, and I'm not sure yet how to use it. So let's put this tab over here. Can I do this? No, I can't switch them like that. Come on, Emacs. All right, that's fine. Okay. So I don't need these two, and I want to go back to NFS. Let's just go back to the NFS folder. Okay, so there's three folders here. One is NFS, one is NFS common, and the other was NFSD. So let's set this up properly again. NFSD is going to be the daemon, essentially the server. I assume NFS, just on its own, is going to be the client. And then common is going to be the common stuff. And since we have the ability to do tabs, let's just open the questions about NFS tab here. And so let's look at common first. I think this is going to be the smallest. We have only 1, 2, 3 files in addition to the make file, but we can ignore the make file because it's not that cool. And the 3 files are SSC, which I think is some either IBM or Red Hat protocol for security. We'll look that up in a second. And then Grace, who knows what that is? This is locks start grace. So there's something about grace periods. NFS v4 grace periods. Okay, and then we have ACL, which I'm going to guess is access control. The Solaris NFS ACL protocol represents some ACLs slightly differently than POSIX 1003. Is that an L or an E? Or a 1, I mean, 1E. So for example, minimal ACLs always have an ACL mask entry, so they have 4 instead of 3 entries. The ACL mask's entry in such minimal ACLs always has the same permissions etc. So we have some sort of ACLs that are represented as masks. I'm guessing like a bit string. And this is stuff to handle ACLs. Let's just peek through and see if there's anything super interesting. Stream encode ACL. Encode an NFC v3 ACL. You get an XDR stream positioned to receive an encoded ACL. What is XDR? I don't know. So let's find out some of this stuff. Let's go over to this tab, I guess. So XDR is one thing. Did I type that correctly? No. So XDR and then, what was it? SSD or SSC? Protocol, let's try. Extended detection and response. That might be what it's about. Let's try XDR stream NFS. Server-side XDR. I've gotten stuck on the idea of rejecting RPC messages where the RPC record is larger than the RPC message itself. All right. So we have some RFC. Is XDR in the RFC? Okay, external data representation standard for NFS, version 4. Okay. Unlike earlier versions, the NFS version 4 protocol supports traditional file access while integrating support for file locking and the mount protocol. So mount, I guess, they're calling it a protocol. I don't know if mount is specifically a protocol of NFS, but let's take a look at that. It's in all caps, so maybe it's, a pun on regular mounting. In addition, support for strong security and its negotiation, compound operations, client caching, was this not available before v4? And internationalization has been added. Okay, so, but what is XDS? XDR. The XDR description is provided in this document in a way that makes it simple for the reader to extract it into a form that is ready to compile. The reader can feed this document in the following shell script to produce machine-readable XDR description of NSF. Okay, so you can sed a bunch of stuff. I guess you're looking for things that start with these triple, this stuff, the triple slashes. I don't know what this is. So let's ask Gemini, what, in the context of NFS, what is XDR and why should we care about it? It's something about the representation. I don't know if it's the serialization of stuff or whatever. Synchronous serial services, maybe SS. No, that's SSI. What about NFS, SSC? Let's just go to Gemini. So external data representation is the standard to describe and format data for exchange between different computer systems. Here's why XDR is important. Interoperability, foundation for RPC. NFS relies on another protocol called remote procedure call for communication. But which are RPC? XDR serves as the data exchange format for RPC messages within NFS. Okay, so we have some sort of RPC system. I'm not sure yet what it looks like, but XDR is, it sounds like maybe it's the serialization format or something along those lines. I'll ask, what RPC system does NFS use? It may just be called XDR, but look, maybe we can take a look at it. We have, this seems to be what they said was going to be the XDR thing, because it says we can extract it using sed. And it has things like file handle size, I'm going to guess is what FH size is, verifier size, I'm not sure what a verifier is, some opaque limit, max int64, etc. So I guess everyone's on the same page about what the biggest int is and all that stuff. And we have some enum for file types, whether it's a regular file, a directory, symbolic link, those sorts of things. And it's kind of that's kind of like meta information about what kind of file we're dealing with. A bunch of error statuses, status, stata. So we have okay. Everything is okay. And then also like the caller doesn't have enough permissions, no such file, a hard IO error, no such device, etc. These all look eminently understandable and reasonable. Move to the file, I guess, is relocated. And then we have basic data types like a bitmap for, a change ID for, a client ID. These all seem to be variants on unsigned integers. And you can imagine this kind of all being written in protocol buffers if you like protocol buffers. So NFS uses the Open Network Computing Remote Procedure Call, ONC-RPC. Okay. And then the last thing I want to know from Gemini right now is, in the context of NFS, was it SSC? Let's get it right so I don't waste Gemini's time. The server-side copy. It's an optional feature within NFS v 4.2 that allows offloading file copy operations from the NFS client to the server. That is useful because sometimes you have to do a lot of copying, and it's better for it to happen on the server rather than copying it on the client, which may be slower, and then uploading all of that traffic. Okay, so that's server-side copy. That's fun and that's good. So ONC-RPC, I guess, is just Sun RPC. Fine. And let's move along. All right, so this should be server-side copy. Should we see what's in here? We can register and unregister, install the blah, 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 client ops. So that's, I think, maybe just registering the option. And this is maybe just configuring the option rather than like handling the calls, which I guess would probably be in the NFSD mainly. And then in ACL, so the XDR is the RPC stuff. So we can basically add ACLs to RPC entries. We can compare ACL entries. This seems to be security relevant code. So you pass in two void stars, and it does what? I guess it tries to make them into ACL entries. And it looks at their tags, whatever an E tag is, and it subtracts them. And if one is bigger than the other, if A is bigger than B, then we get a positive value back. And I don't know, I don't know what that means, but there's some ordering on the ACLs. I'm not sure if it's asking whether like A can access the thing ACLed by B or vice versa or something else. Otherwise, we look at the tags and see if A is a user tag, and we call UID greater than on the UIDs. So if I guess the thing we're looking at more seems to be A, which comes from X. So I think it's saying like if the thing is a user ACL, then we compare the user ACL on what I'm going to guess is the object to the B, which is what I'm going to guess is the thing trying to access the object. And we want, I guess, A to be greater than B or something like that. And if it's less than, and if we have less than, we get to return -1, which I'm going to guess is reject. And so on with groups. Okay. Something like that. All right, that's fine. So that's, and then we have grace, whatever grace, there's some locking grace period. The grace period is a period during which the locks should not be given out. Currently, grace periods are only enforced by the lock managers, LockD and NFSD, using the locks in grace function to check when they are in a grace period. So I'm guessing grace period is maybe to allow like startup and warm up. but maybe we can find out about that somewhere. NFS lock grace period. How do the grace periods work? What is LIF? So there are two NFS v4 related grace periods. When a LIF, whatever that is moved to another node. So I guess this is some like file data, I assume. So we have some distributed system and, you know, stuff is happening in the background. Like maybe one of your machines is dying or they need to rebalance. So at some point, stuff might get moved from one machine to another, which I assume is kind of what they're talking about with whatever a LIF turns out to be. In that case, I guess you would need to have some way of saying, don't access this file while it's moving or well, until we can ensure that things are good or something along those lines. But let's see what it says. So when a LIF is moved to another node, clients can reclaim locks for the duration specified by the NFS option, v4 grace seconds. When an aggregate is relocated to another node, NLM lock reclamation takes place, blah, 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 blah. After a takeover, the two periods may overlap. Let's see if we can find NFS LIF. Create a LIF. A logical interface? Okay. And let's just ask Gemini, tell me about NFS lock grace periods. They come into play specifically with version 4. Here's how it works. Client locks. So there are locking mechanisms to ensure data integrity when multiple clients access the same file. So this is related to the write complex. A client acquires a lock before performing write operations to prevent conflicts. So the client locks the file. We'll see what happens. So that should exclude anyone else from getting a lock on the file. Hopefully it's the locks are atomic in the sense that you have consistency. Server restart. If the NFS server encounters a restart or outage, client locks might be lost. Without a grace period, clients wouldn't be able to differentiate between a temporary server issue and a lock being released by another client. This could lead to data corruption if a client attempts to write without a valid lock. And then to address this, we have a configurable grace period. This is a window of time after a server restart. Okay, I think that was my original speculation that it was to do with servers starting or restarting. During this grace period, the server allows clients to reestablish their lock state without conflicts. Good for them. Okay, so these locks do things. They prevent errors from happening, et cetera, et cetera. So tell me about, so if two clients try to lock the same file simultaneously, is it possible for both to acquire locks? If not, how is this prevented? I'm sure the answer is ultimately like Paxos. No, it's not possible. So yeah, here's how it works. Locking requests. There's a lock manager. It maintains the lock state of all files and attributes the lock request to clients, granting or denial. Based on the current lock state of the requested lock type, the server will either grant a lock or deny it. So I guess so is there only one NFS master, or do the masters vote? There's no concept of a single master or any voting. Okay, so it's not distributed. It's just a single server, I guess. Fine. The client-server architecture allows for scalability. You can add more NFS servers to provide additional storage capacity or distribute the load across multiple machines. Wait, what? So each machine exports its own file system. Okay. So that's not so scalable, but that's fine. All right. Okay, so that's NFS common. We will ignore that. So how to resolve conflicts, locks. And system is not distributed, which is the opposite of what I said before. So don't need to worry about agreement, I guess I'll say. All right, so let's look at NFS, which should be the client, and also NFS daemon. So which one do we want to look at first? Let's look at, so NFS-D is shorter. Is that a virtue? I'm not sure. Let's look at NFS itself first. So we have this v4 header, which I imagine is mostly going to be about metadata. And it's pretty small. We have things like remove X attribute, allocate, proc copy. Proc copy. I don't know what proc means. Proc allocate, and so on. That is maybe cool, but not the most cool. Let's look at mount client, inode, get root. The cache might be interesting. I'm going to guess fs cache is the cache. We also have cache lib. We have some callbacks. Client.c, dir, I'm going to guess is directory. We have DNS support, which I guess I'll ignore. File.c, file layout. Maybe we'll look at the file layout header. And what else do we want? I think that's going to be about enough to get us close to where we need to leave. We have syst control. Is that interesting? Write, I guess we should look at. And read. Maybe proc. And then over on the NFS-D side, I'm curious about ACL and auth. I'm pretty sure NFS only uses... Let's see if they have if there's anything about Kerberos. Against AD, is NFS with Kerberos worth it? Looks to be a real pain to set up. NFS authentic. Let's do authentication. Securing NFS. However, with the easy comes potential security problems. To minimize NFS security risks, considering the following sections: security with auth sys and export controls. NFS security with auth GSS, configuring Kerberos. Okay, it seems mainly like some settings, like access control settings, and then if you want like real security, you would use something like Kerberos. Okay, and then we have this file cache on the NFS-D, which I guess is like the server side part of it. Lock-D is possibly interesting. NFS-D itself. XDR, I guess, is the representation. XDR4 is probably the more recent one. VFS, I'm going to guess, is the virtual file system. Stats, I'm not sure what that is, but we'll possibly look at it. And I think that'll be enough to take us well over an hour. Okay. On to NFS. I think I want to look first at, let's look at read and then write. Block IO for NFS. Partial copy of Linus's read cache modifications to fs/nfs file.c. Modified for async RPC by Oker at monad.swb.de. All right, so what are we? We're in a C file, not a header file. And we've got some static functions that have to do with headers. So NFS, I guess, page IO header, and this NFS read header alloc is going to call zalloc, and it's going to, whatever P is, I guess the thing, so we're going to, I guess, allocate this header, and if we get it, we're going to set its read-write mode to read. So that's fine. And NFS header free. So this is going to be freeing stuff, whatever empty folio is. We've got some whatever. There's something called a folio, and we're going to, I guess, unlock it and free it and stuff like that. So we have page IO init read, which I'm going to guess is going to initialize the read page IO descriptor with an inode, which is like the like metadata for the file. Whatever force MDS is, some like flag essentially, and then compl ops, NFS page IO completion ops. So I guess we get some completion back that I guess we can execute. And so I'm going to guess page IO is NFS specific. PGIO NFS. Announcing PGIO, the slob method for Postgres. It's not Postgres. There seems to be some name collision here. Initiate PGIO. Maybe page IO NFS. I don't know. I'm going to guess that's what it's for. Okay. At any rate, we call NFS server on the inode, which I'm going to guess is just going to look up the server that like handles that inode. Let's see if we can find it. This thing. NFS server is going to return NFS SB. We're going to take the inode and look up the whatever SB is. And NFS SB is going to, it's the super block. It's going to look up the super block, and we're going to return the NFS server struct. No. We're going to take the super block and just peek into its SFS info thing, and we're going to cast it as an NFS server. So I guess the super block knows which server is serving it, and the inode gets that information from the super block ultimately by chasing through pointers or whatever. All right, so we get the server from the inode, which was the thing we passed into read, and this NFS PGIO RW ops, is that passed in? No, but we create this PG ops struct that I'm going to guess is the thing that maybe we return eventually somehow. And if we were in, I guess, v4, assuming that's what config NFS v4.1 means, we're going to look in the server, whatever PNFS is, the current LD, and maybe check whether we're forcing MDS. And if we're not forcing MDS, then we're going to set page ops to the thing that we get from server looking up cur LD and page read ops. So the struct just has the things that we need, I guess. Otherwise, or I guess regardless, we're going to call NFS page IO init with the page IO stuff that we passed in, the page IO descriptor, the inode, and some other stuff. And that's it. Whatever NFS page IO init is doing, initialize a page IO descriptor. We have a pointer to the descriptor, et cetera, et cetera. So we set some stuff on the descriptor. Oh, this is just initialization, like we're just like zeroing some stuff out. Okay, so that's really all it's doing. It's basically just looked up but what have we returned? We've returned nothing. What is compl ops used for? So we're passing in compl ops, I guess. I don't know if this is in or out. Okay. At any rate, that's like just an initialization function. And then complete read is we've got an NFS page IO mirror and some number of pages that is not passed in. And we call page IO complete on the page IO descriptor that was passed in. And then we call warn on once. It doesn't make sense to do mirrored reads. If the mirror count's not 1, then something went wrong, I guess. And then we get the mirror at 0. I'm guessing maybe mirrors are more for writes then. So we get the first mirror, and that's now PGM. And we increment it by bytes written. And then we call NFS I on this I node. Rather we, yeah. The thing that we're incrementing is the read IO variable here. And then we set end pages to this computation that just says we consumed some pages. And then we call NFS add stats. But where did we actually do the reading? Is that in page IO complete? Complete IO, then clean up an NFS page IO descriptor. I think this must do the reading maybe. Whatever mid X is, we've got some page IO descriptor, and we are going to iterate over the mirror count, and M index, I guess, is what this is supposed to be. And we're going to call complete mirror. And I'm guessing complete mirror is the function that is ultimately going to do reading or writing. And then we're going to check for errors, and then we're going to clean up mirroring. So let's look at complete mirror. Complete IO on the current mirror of an NFS page IO descriptor. Okay, so we've got some mirror and a descriptor and some mirror index. Restore index. Set current mirror. So we're going to set the restore index somehow from the current mirror index, and we'll create, and mirror will be the thing we get from this variable. And then we have an infinite loop, and then we're going to call NFS page IO do IO on the descriptor, and then check for errors. And this must be the one that really does IO, considering they named it do IO. So it gets a descriptor, it gets a mirror, and if the mirror list is non-empty, then we're going to call on the descriptor, we look at the page ops, and then we look in the page do IO thing, I guess, which must be a function, and we pass it the descriptor, which it already was. So this seems like this, it must already have this information somehow. And then we check for errors. And so page do IO should be a function, right? So it's a, what am I looking at? We have this struct, and this is I guess a function that returns an int that takes in this descriptor, right? And what does it actually do? Do we get an implementation anywhere? Maybe. What? End of file during parsing. What kind of world do we live in? Let's try GitHub. So here, this is maybe setting PNFS generic PG read pages. So I guess this is, if we are, this may be an implementation. So we have some page header. So we pass in the descriptor. We create some header and some return value. And then we call NFS page IO header alloc to allocate a header. If we don't have a header, then we have some error. And then we have header init. So we initialize the header, we get an else egg. And then we call NFS generic PGIO and get the result. I'm guessing generic PGIO, we're just chasing down to see if there's anything that actually reads data or if it's all a charade. Generic PGIO. This is the header. So internal. Let's look at internal. Internal.h. So here's generic PGIO. Create an RPC task that's promising for doing reading for the given read or write request and kick it. The page must have been locked by the caller. It may happen that the page we're passed is not marked dirty. This is the case if NFS update page detects a conflicting request that has been written but not committed. Okay. Okay, so we have the page IO mirror, etc. NFS page, list head, commit info. And we have page count. So we have this NFS page array, and we're passing in page base and mirror page count. So that the count we get from the mirror, whatever the page base is, I'm sure we made it up here. And if the page count is less than or equal to the array size of the page array, then we set the page vec of the page array to be the pager, the PG array page array. I don't know what that is. Those variables are all confusingly named in a similar way. So this, I assume this is something like if we don't have enough space, we're like adding more space or something along those lines. Otherwise, I guess we do have enough space, and we set the page vector. No. I guess this means we do have enough space. This is we don't, so we're going to allocate some stuff, I suppose. Then we call init cinfo, which maybe means we're ready to make a call or something like that, along those lines. We get the page vec, last page is null, page used is 0, while the head list is non-empty. We do some more stuff with pages. We get the list entry and the NFS list move request. And if the request WB page base is 0, the last page is null. NFS page iter page init, while page is equal to NFS page iter page get if last page is not page use plus plus. I don't know yet whether any of this is doing work or if we're still kind of preparing to do work. And then we call NFS page IO error here if the page use is not equal to the page count. And this looks maybe like this is like flushing. So I guess we're done if we're down here. Set up the argument struct. So here's what we call NFS page IO RPC setup. Given the header, the page base, the mirror, page count, IO flags, and cinfo, and then we call PG RPC call ops. Oh, we set the ops. So this is creating a set. This is creating the RPC. It says in kick it. Does kick it mean send it? Because it seems like we called the setup function, setup arguments for a page IO call. How to commit the data, writes only, commit information, writes only. Okay, so this is the thing that sets up the RPC call. We have things like the, I guess, file handle, offset, PG base, pages, count, etc. context. So then like maybe file attributes, etc. So it seems like, so where did we start? We had some inode descriptor, and we have to figure out things like where is the NFS server, and we look up in the inode description to get that, it seems like. And then we chase through a bunch of other stuff that's like setting up this bit of information and that bit of information. And then ultimately we get down to an RPC call. That RPC call has to, for this to have any sort of efficiency, it has to essentially tell the server like where, ideally like where physically on the disk is it, like, and I think that that's more or less what it's doing. We have some page base and some page offset. So it's like I'm guessing it's like read a specific page off of, like when this was written, it would have been mainly, I think, spinning storage. I don't know what storage was like in the 80s, but it wasn't better than spinning disk. I mean, yeah, it wasn't like SSD or anything like that. So I think this was, I think that's the sort of thing it's doing. What I don't know though is what is that generic? It seems like we created this RPC, but I'm not convinced that that we sent it. Maybe this sends it, but I don't see how. Common op. We're just setting the call ops to this thing. So I think it's going to be too impossible to unravel exactly where we were. But maybe. How about NFS page? No, I don't know. Well, that was read, right? That's what we were ultimately doing. So let's read. Let's take a quick look at write and see if we uncover anything else, anything less mysterious. So writing is going to be harder because you have to care more about locks. So we have like this completion init, completion release, and completion get. So there's, I'm not sure really what's up with the completions, but I'm going to guess, well, let's tell me about completions in the NFS code base. I'm going to guess they're kind of just like callbacks. Like there's more work to be done. Maybe you read only a bit of the file at a time, and then you get some kind of like handle back that you could redeem for further reading. Completions typically refer to a mechanism used for asynchronous I/O operations. NFS, being a distributed file system protocol, often deals with operations that might take a significant amount of time to complete, such as reading or writing. So they're making it sound a little bit like promises. In the context of NFS code, completions are often associated with asynchronous operations, blah, 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 blah. It's typically created to keep track of its progress. Once the operation completes, either successfully or with an error, the completion object is signaled, allowing the code to initiate that initiated the operation to proceed accordingly. Okay, so that's basically describing more or less the idea of a promise. So you get some object, and the object is going to like let you know somehow when it's done. Okay, so we have this folio stuff. We don't know what a folio is. NFS folio. I guess a folio is a collection of pages. I'll say in NFS, what is a folio? Used for managing memory pages. Okay. Traditionally, the kernel manages memory pages using a struct page data structure. However, the structure has some limitations, particularly in terms of memory overhead and cache efficiency. Folios were introduced to address these limitations by providing more memory efficient and cache-friendly representations of memory pages. In the context of NFS, folios may be used in various places where memory management is involved. So when NFS code talks about page I/O, is that memory pages or pages on the disk, or both? I guess. Page I/O, which generally deals with I/O operations involving memory pages rather than disk pages. Okay. Related to reading to memory pages that contain data being transferred over the network. These memory pages can represent various things. Okay. So on the server, the data is typically read into memory pages on the client side. Whoa. When NFS client reads data from the file on the NFS server, it's typically read into memory pages on the client side before being processed or written to disk. Right. When it writes to the server, the data is written first to memory pages. Okay. So how does the client know anything about the disk layout, or is it only concerned with the memory layout? Okay, so ChatGPT is saying that the NFS client is only concerned with the memory layout. Let's slightly decrease our chance of hallucinations by asking Gemini the same thing. So memory pages. Okay. So NFS operates on files, transferring between blah, blah, blah. PJIO stands for page IO. page input output. This refers to the process of moving data between memory pages and other locations, typically storage devices. Code focuses on the client side. The NFS kernel code using page IO primarily focuses on the client side. The data transfer between memory pages and the network for communication with the server. While NFS ultimately interacts with data on the server's disk, page IO functionality itself is concerned with managing memory pages on the client system. Okay. All right. So then that would make sense given that Folio is apparently also related to memory pages. And so unsurprisingly, we have things like now lock requests. So Folio find and lock request. We give it some Folio, and we're going to have a lock, right? How about highlight? So NFS page group lock head, NFS unlock and release request head. So what is head? Head is something. We create it here and it's empty. Find head request on the Folio. So find head request associated with the Folio. Returns matching head request. What is a head request? NFS head. What is a head request? The search engines don't seem to be the place to go. A head request is a special type of request. No. In the context, what is a head request in the context of NFS? What? Find head request must be called about matching head request. I'm not sure. Let's try ChatGPT just for in the context of NFS. What is a head request? To retrieve metadata about a file or directory without transferring the entire file. Okay. Well, yeah, maybe. At any rate, we've got locking, and that's, I guess, going to be the main difference. We've also got grow file, I guess, what you also need to do if you're writing. Adjust the file length if we're writing beyond the end. And how do we do that? We've got some Folio file mapping, and we get the host, and that's going to be an inode, I guess. Why is the host an inode? I don't know. And then we have some spin lock on the inode. On the inode's ilock, and which seems like we're not accessing the remote server. So this seems to be maybe just a local lock. And then we're going to read the size, get the end, I guess, and we're going to you may go to alt, I guess. There may be some invalid size. We're going to file unlock if we're down here. We increment stats here, and trace NFS size grow is called here. I don't know what trace means. Maybe trace means that we're going to call the thing in a traceable way. See if we can find this on GitHub. Well, I don't know. I did see some code for NFS tracing before. NFS trace is a NFS and CIFS capturing analyzing tool. I think that maybe we're going to essentially call size grow, maybe with some keeping track of stuff for tracing is what I'm going to guess that's trying to refer to. All right, so that's write and read. We have a little bit of a sense. We're not going to get too much of a sense because we're only going to be here for an hour, and it's a pretty big project. File, I think we've looked at just a little bit. I think this is where the reading logic ultimately was. We have open file, which I guess we're going to print some stuff out, log some stuff out that we're opening a file. I guess that's so you can track who's opening what files. We're going to increment stats, saying that there's now at least one more open on this particular inode that we tried to open. And then we're going to check some flags. And if we get a result, we return the result. I don't know. I guess we haven't opened then, right? Because how could we have? Otherwise, we call it NFS open with the flags. And if we get a result, then if result is 0, and then we set F mode can O direct on F mode. I don't know what that means, but NFS open seems like it's doing the work. This is an inode.c. These allocate and release file read-write context information. So we allocate some stuff. If there's an error, we do some stuff. Otherwise, we call NFS file set open context. Then we call put NFS open context, and then NFS cache open file. Maybe cache open file is the thing that does network I/O. So I guess it would make sense that the first thing maybe you try to do is open it in the cache, and then if the cache fails, maybe it sends network requests or something. Enable or disable caching for a file that is being opened as appropriate. The cookie is allocated when the inode is initialized, but is not enabled at that time. Enablement is deferred to file open time to avoid stat and access thrashing the cache. Okay. I don't know what enablement means, but it sounds like we want to avoid somehow stat is going to behave badly if we that is being opened as appropriate, is allocated when it's initialized. Okay, so I guess that at some point it's initialized, but now it's being opened. And so now we're like enabling it, I think is what it's saying. So open file, we're going to have some aux data. We get the cookie, which I guess was created at initialization. And if it's open for write, we get that variable here. And if the cookie is not valid, we return nothing. And otherwise, we call fs cache use cookie, saying that it's open, saying whether or not it's open for write. And if it is open for write, we're going to call fs cache update the aux data with the inode information. And we're going to invalidate, I guess, some stuff about reading, saying that like I think this is maybe saying that like stuff may have changed since you read or something along those lines. Okay. And then we have release file. NetFS read ahead. Okay. Init request. I still don't see yet really where there's like a clear boundary between things that happen locally on the client and things that go all the way out to the server. So let's take a moment here to jump over to the server. I wanted to look at ACL and auth, but maybe let's look at a file cache since we were just on the client file cache. So we have some FS notify mark container that NFSD attaches to the files that it is holding open. So I guess we have some sort of marking that when we're holding open a file, note that we have a separate ref count here, aside from the one in the FS notify mark. Okay. So we have the struct for an NFSD file, a representation of a file that has been opened by KNFSD. These are hashed in the hash table by inode pointer value. Note that this object doesn't hold a reference to the inode itself. So the NF inode pointer should never be dereferenced, only used for comparison. Okay, so this is just some, essentially, it sounds like this is a hash table, keeping track of the files that have been opened, but this is just like an index rather than the files themselves, or it doesn't have, it doesn't represent the contents of the file anyway, just like what's open. And then we have a bunch of functions like initiate the cache, purge the cache, acquire GC, maybe like garbage collect, etc. Okay, so that's the header. The implementation is going to be more involved. We have this credential matching. This logic looks a little bit like the ACL logic that we saw in the other file. We have some things like FS notify group, kmem. I'm going to guess is kernel memory. I'm not sure. Schedule laundrette. Is that like laundrette? Sounds like maybe it's some sort of garbage collection. Some stuff about slab allocation, it looks like. And this is going to be, so all looks pretty memory related, as you might expect from the cache. We have an LRU cache of some sort, at least recently used. NFSD file LRU add. And then LRU remove. We're going to call this other delete operation, which I guess is going to take care of finding out which files to remove, etc. Okay, and then should we look at lockd? I'm not sure if this is going to be understandable. This is just going to be locking stuff. Lock init, lock shutdown. Okay. Maybe let's look at nfsd.h. Common arguments, common void arguments, function prototypes. So NFSD service, I'm going to guess this is like the serving function perhaps. You give it some credentials and some net thing and nr serves. Some dispatch function. Somehow it's got a dispatch, I guess, request to various things. I don't know if this is dispatching to other machines or to like physical devices or whatever. Some stuff with threads and pools and stats. This is all servy, classic servy stuff. This looks like slab allocation, shutdown stuff. Whatever laundry is, which I assume is related to laundrette. And then lock stuff. These are macros. These provide pre-RX XDR values for faster operation. So these are the error functions that we saw before, but it sounds like these are like XRD'd in the sense that these are like the byte, like the network byte representation as opposed to the C representation, and they're just ready to go. You can just append or insert them into the network request for faster operations, so you don't have to convert them. Then we have some stuff like for compound operations, supported attributes, like F attribute word0 change, word 0 change, ACL support, case preserving, files available, ACL, max write, least time. So these are some sort of file, it looks like attributes, or maybe these are configuration options for NFS. Okay. That's mostly understandable. We're just whizzing by. I modified it? No, okay. I guess let's look at stats. Stats are just statistics. So we've got some counters per CPU counter. So I guess we're going to keep track of it per CPU. We've got RC hits, maybe remote cache hits. It seems to be cache related. So cache hits, cache misses, I assume, memory usage, etc. IO write add, how many IO write, and so on and so forth. Okay, and then VFS, I'm going to guess is like virtual file system stuff. So we have the I attributes, the XDR net object, some POSIX ACLs, and some labels and an ACL error, I guess. And attribute free, and we should have things like, yeah, here we go. I think this is like, do we have things like seek? You should have, do we have F open? Do we have open? So we have NFS open. It's going to take a service request a service file handle, a mode, an int, and a struct. Let's see if we can find an implementation. If we get here, then the client has already done an open and hopefully checked permission. So allow owner override in case a chmod has now revoked permissions. Okay, so this should be essentially some implementation of open, except we have this other stuff at the beginning. Let me look at the open system call. So open takes a path name, some flags, and a mode. We have a mode here, I think is what that's supposed to be. File, I'm going to guess, stands in for the path. And then some flags, may flags. So I think this is supposed to be an implementation of the Unix system calls. Setx attr. Setx attr. Set an extended attribute. So this function takes a path, a name, and a value, a list of values, a size, and some flags. And this should be basically the same. We have the service request and the service FH, name. This must be the values, a length, and some flags. Okay, so these VFS.h I think is the essentially the implementation of the Linux or POSIX file system interface. Here's XDR, which should be the like the RPC format, if I'm understanding correctly. We have things like the NFSD file handle, which is the service FH. Oh, no, rather. This is a service FH is a struct. Let's see if we can look at the struct. This is the internal representation of an NFS handle used in KNFSD. Pre-M time post version will be used to support blah, 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 blah. Okay, so we have some file handle data. I don't know how this is different, but I'm not going to chase it on forever. We have some maximum size, a D entry. I'm not sure what a D entry is. I think it's some Unix thing. D entry is the glue that holds inodes and files together by relating inodes to their file names. D entries also play a role in directory caching, which ideally keeps the most frequently used files on hand for faster access. So it's some Linux filey thing. And then an export pointer. Not sure what that is, but so there's whether we want to write and something about remount protection. Whatever WCC is, but also flags, post-saved, pre-saved, size, etc. So this is some NFS specific version of file handles. And then we also have things like the IATR stuff, attributes, and so on. Read arguments, create arguments, rename. So these, I guess, these are arguments to the rename function. When you rename something, you're going to give it a service file handle, a file name, a file length, something, TFH, some other file handle maybe, and then name and length. And then these, I guess, are probably the functions, right? Or no, these are, I guess these are decoding stuff, like decode file handle arguments. You give it a service request and an XDR stream, and it will tell you if the decoding succeeded. And it's just going to try to take the XDR stream. Where are args coming from? And args we get from the request. So it's going to take this thing in the request, get its args, and try to I guess XDR is probably the out parameter then, and then it's going to try to I guess put this into the XDR stream. Let's see if we can look at the service request. The context of a single thread, including the request currently being processed. The context of a single thread. is the service request. So we have a list head, all threads list, an idle list, RCU head, a transport pointer, some socket stuff, including the peer address, the RPC service definition, a thread pool procedure info, authentication flavor, so some sort of authentication info, credentials, I guess. Deferred requests we are replaying, and then an XDR buffer and some pages, and so on. A folio batch. So this service request is there's a lot here. I thought it was going to be a single request, but it's like it seems like it's everything. Oh no, maybe not. Maybe this is all a single request. Okay. So that's beginning to look more like RPC stuff, and we're doing in some way serializing, deserializing RPC, and that's maybe a little bit like, again, proto buffers is the one I'm most familiar with, but there's a bunch of RPC protocols. This seems to be, if we believe, I think, what was it, ChatGPT, this seems to be basically Sun RPC. All right. What else do we want to see? And how long have we been here? We've been here about an hour. I don't think I'm going to go too much longer. Auth, I just kind of want to see if there's anything. Not much. We can set the user. Set user. I don't know. I'm guessing this is just using the existing Linux users, or Unix users rather. And then ACL, I guess NFS has its has some idea of an ACL. I don't know if it's the same as the mode of Unix, or if it's something else. Block layout. Should we look at block layout? Block volume, random upper cap on the UUID length. So I don't know if this is going to be informative. We have some block volume type, SCSI code set, length, number of SIGs, offset, SIG length, struct that has start, length, and volume, volumes count, and this is a stripe. A stripe has a chunk size, volume count, etc. We have a block device map. And I don't know enough about the Linux file system to know really how this is used under the hood, but this is starting to look like this is a way of representing block devices. We see things like offsets and slices and those sorts of things. And we have an extent tree, and we can insert and remove from the extent tree. So if we're going to insert something into the extent tree, we have a block layout struct, and then we get back this new extent tree as an out parameter. This block layout struct that we passed into the extent tree has some roots. So I guess this is like read-write stuff, read-write extents or read-only extents, or something along those lines. And I think that's maybe about it. So maybe the last thing I'll do is I'll ask about file system extents. I'm not really sure what in particular an extent is. So we have data files, pages, and extents. So it seems to be for some database, but we have a page header, some rows, and some free space. Here's what appears to be a model of a spinning disk. We have file system metadata, and then file system data, equal sized allocation groups. I guess these are like sectors of equal size on this annulus that is a disk. But what is it? What is an extent? Here's an X4 inode as an I block. some header, a root, and it points to other things. And this is beginning to seem familiar. So I guess there's some index node, which is going to point to the leaf nodes. And you like walk along the extents to get to the specific parts of the disk. Let's ask Gemini. Tell me about file system extents in Linux. Extents are a way to track where data for a file is stored on the disk. They essentially act as a shortcut for the file system to locate the file's data efficiently. Here's a breakdown of how they work. In traditional block allocation, XT would keep track of the file's location by storing a list of individual disk blocks the file occupies. This could get long for large files, requiring more storage space for the file system's bookkeeping. Extents came in to address this inefficiency. Instead of storing a list of every single block, extents group contiguous blocks into sections and store the starting block address and the number of blocks in that section. So this is just, this sounds like it's just like if you have, this is just like standard encoding. So if you have something like this, you encode it as like I'm not going to count, what is it, E4, F4 or something like that. All right. Okay, so draw a impressionist painting of extents. What? Make it look more like a file system. Okay, that's a little bit better. All right, so that's all for me. That's NFS. Again, like all of these big projects, we really just scratched the surface, but we have a little bit of an understanding of how the code is organized, what's going on there. In the client, one thing that kind of stood out to me was you have to dig really far before you get anything that's like a network request. And I don't know. And so in a sense, that makes sense, because kind of what that implies is that a lot of what we saw was juggling around the metadata, making sure, like essentially computing from the user intent, like the user wants to read some particular file. Well, we've got to figure out how that translates into a request that's made over the network. The less we have to send over the network, the better. So a lot of the client seems to be about, from the perspective of like the coders, it seems to be about putting the network request maybe in a small area of the code base, and kind of like everything else is about the intelligence of the client. It seems like that's my impression. The NFSD server itself, that seemed more straightforward to me. It's basically, it has models for all of the things that you would expect there to be models of. Like it has some model of the file handles. It has some way of modeling the Unix POSIX system calls. And then the other thing that I was curious about and was answered was like what sort of language is it speaking over the network? And it's some variant of RPC. If we believe the AI overlords, then it's Sun RPC. And all of that was interesting and informative. And that'll be all. Thanks for watching.